Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. We're continuing down the path towards understanding the Big Bang and some of the more important elements to it. We're not going to get into huge details like we're taking a graduate level course or something, but I'm giving you a taste of all the things that go into Big Bang cosmology. One of the most important things that we have then is that we found last time that galaxies come in clusters and groups and that there's been some big surveys. So now we're going to look at galactic evolution and how things change. So again, cosmology is the physics and distribution and age of the universe. And the cosmological principle says there's nothing special about our location other than it's our place and our home. And as a result, the laws of physics are the same everywhere in the universe. All right, so what is out there way out past 10 to the 8th parsecs, 100 million parsecs in the billions of light years? What do we see out there? Well, what we can do is we can actually look far back in time and use very specific kinds of surveys to see how galaxies have evolved with time. And that's really what we're going to be talking about now. So it's thought that galaxies go from small, misshapen, extraordinarily blue objects and go by mergers and mergers and mergers into forming spirals and giant ellipticals. So it's thought that galaxies start in very tiny things and grow through gravity. And that's what we think it is. Now, given that's the concept, we should look for that in the observational evidence to see if this general sketch is true. So we can also think that there's definitely evidence for collisions because as we saw, starburst galaxies have massive star formation. We can actually model the appearance of starburst galaxies by colliding. And the collision models and numerical models that show collisions between spirals can actually accurately map objects that we see deep in the sky. And in fact, we see some places that look like they have multiple cores, like some galaxies are supermassive giant elliptical galaxies and appear to have multiple galactic cores, and so they must be in the process of merging. Also, we know about stellar streams. There are stellar streams around other galaxies, and there's also stellar streams orbiting our Milky Way. And stellar streams are tiny little galaxies that are very low mass that get spread apart along the line, their orbital path, and as they orbit, they get stretched and pulled, and their stars get pulled into different orbits, and they no longer look like a galaxy, but now look like a stream because of the tidal pull between the near and far side of the little galaxy. So we should expect that larger interactions actually will create maybe some spiral interactions, maybe a small galaxy turn a large one to a spiral if it still has gas and dust, if it spins it up. So we can then say, well, do these evolutionary characteristics actually appear in the data? And so if we look at massive surveys, such as the 2DF Galaxy Redshift Surveys, looked at about 250,000 galaxies, and they showed that, yeah, they're distributed in sheets and filaments and voids, and what's been looked at by this specific survey goes out to about almost 2 billion light years. And there we'd have a better view of it. And we see the redshift is about 0.25, or about a quarter. And that's a really good way of measuring. Instead of billions of light years, redshift is the big thing that we're going to be talking about. So the other one that's actually been a significant contributor to the universe, our understanding of the universe, is the Sloan Digital Sky Survey, which was a large 2.5 meter scope in Cloudcroft, New Mexico, and I actually went to grad school in New Mexico State, and I started off the very, very, very beginnings of the elements of the computer technology that went into the stuff. And so back since that's the early 1990s, we're talking this is like the beginning of the internet. So nowadays it would look what I did was kind of minor, but yet it was groundbreaking in its time. And that's how it helped me to do other things in my life too, which is kind of neat. So this particular telescope, though, the Sloan Digital Sky Survey, which is shown here, its goal and its major survey ran from 2000 to 2008, and it cataloged millions upon millions of objects with hundreds of thousands of quasar redshifts and lots of galaxy redshifts. And it got photometry for billions of stars, galaxies, and quasars. And the goal with this thing was to make an accurate map of the sky and specifically hunt for galaxies on their redshifts. And there it is over the Sacramento Mountains, and in the distance you can see the White Sands National Monument. So this is a beautiful place, and if you ever get a chance to go to New Mexico and get up to Cloudcroft and say hello, do it. Anyway, this is one of their data sets. This comes out from the Sloan Digital Sky Survey. Comes from what they call their classic legacy archive, and it shows out to a redshift about 0.15, which is not as deep in this particular image as the 2DF survey. But over time, the Sloan Digital Sky Survey went much deeper and had much larger data set than 2DF. Well, what can we find that takes a little bit? So let's go back a little bit further and see why the Sloan Digital Sky Survey was even done, and why 2DF was done, and what motivated people to make these massive surveys. Well, the Hubble Space Telescope was launched a while back, and one of its major goals was to actually study the evolution of the universe. And what this was the longest at the time. It was released in January of '96. It was the deepest survey yet done by any telescope ever. And so this is what we call a pencil beam survey. And the Hubble Deep Field allowed us to see galaxies back to about almost 13 billion light years in distance. But we see that there's all sorts of arrangements and appearances to galaxies. There are about 1,500 galaxies in this image alone. But remember that the size of this image is very tiny. It looks kind of big here, but if you take a dime and put it 75 feet away, that is the size of this image in the sky. So it's a very, 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 very tiny image of the sky. And if 1,500 galaxies are in this direction of the sky, then they're everywhere. And this is not the deepest of the surveys, but this was the first one. And here's some elements from it. And it was the details was pretty controversial when it first was done, because nobody actually thought that this would actually use Hubble time wisely. But it ended up being an amazing, amazing set of discoveries. And we see most of the objects in here are galaxies. There are some faint red dwarfs that are Milky Way objects. Those would be the stellar objects that are in the foreground. But most of the tiny, tiny, tiny objects in the background are galaxies. Again, here are some more details from the Hubble Deep Field, and there were 342 frames taken over the course of 10 days. So this is a huge, huge undertaking, and the size of the area this was one of the longest exposures ever done to date in 1997. All right, so. But that wasn't the first then. Considering that was something that actually yielded results, then people said, well, let's keep going. Let's keep going and get more. So the Hubble Ultra Deep Field, based in part on that, surrounding that area. And so what you see is the purple circle here shows what the Hubble Ultra Deep Field looked at, and that the circle illustrates the size of the moon. And then there's the green outline, which is the GOODS survey, and this is the GOODS North group. And so there's a very large image that was created out of that. And the advanced camera for surveys on Hubble Space Telescope is a tiny little blue block in the center, and the near-infrared camera and multi-object spectrometer, or NICMOS, also on the Hubble Space Telescope, was used to do deep imaging. So a series of images were given in this whole area in order to discover exactly how deep, what kind of depth we have. And the Hubble Ultra Deep Field then was released in 2003, about 6 years later. And this also contains the Hubble Deep Field, but there's now 10,000 galaxies in this visible light image, and so they used so now the visible light band was used. And there are some very, very, very red galaxies. And the dimmest objects and tiniest galaxies were when the universe was only about 800 million years old. And so as you see when close-ups of this image show that when you look at deep, deep, deep into this image and look at the highest redshift objects, then those are small blue misshapen galaxies. And you only get fine structures like spiral galaxies in the local universe, meaning today. And there's something really interesting about this that we'll get to. But this again was an enormous undertaking with 800 exposures, taken over 400 orbits of the Hubble Space Telescope around the Earth, about 11 days of exposures. And this utilized the advanced camera for surveys. And then they utilized looking at, with the NICMOS experiment, looking at the near infrared, to actually look at the objects who would be strongly redshifted. And this gives an important element to see what are the deepest objects in this field, and that allows you to see further back in the past, because if something's getting greatly redshifted, it will probably appear in the infrared rather than visible. And so you can actually see farther back in time using this, and that's why the caption of this shows that it's about 400 million years after the Big Bang would be the deepest and faintest objects inside of this. So the Hubble Ultra Deep Field is actually in the northern constellations. Actually, no, this is the Hubble Ultra Deep Field south. It looks in the exact opposite direction. And we're looking in the area of Eridanus in the constellation Fornax. So there are many details in the Hubble Ultra Deep Field that show the evolution and state of galaxies. You can see some extraordinarily misshapen objects, and only the larger objects, meaning the closer objects, meaning objects that are in the local universe, are actually things that are grandly structured, such as spiral galaxies. But if you look in, say, the lower right image of these six, you see in the kind of the right left-hand side of the lower right object, you see a really distorted and misshapen thing. In fact, all the objects in there are distorted and misshapen, and only recent objects, meaning very nearby and at low redshift, have the appearance. And what we're actually beginning to see is that something that looks like the Milky Way only appears now. If the universe was infinitely old, then we should expect to see things just like the Milky Way, but extraordinarily far away. We do not see that. What we do see, though, is the Milky Way is only a recent thing. And if we look farther out into space, and therefore farther back in time, we see that there is an evolution of galaxies from then to now. And we do not see anything in the deep, deep, deep past that looks like anything like the Milky Way. So this is, again, a prediction of the Big Bang, that there would be a baby picture of the universe and an adult picture. And baby pictures predict that if the universe had a beginning, then if you look farther out into space, you're looking farther back into time. And therefore you should see things as they were ago. And if the universe was infinitely old and didn't have a birthday, then you should see Milky Ways and things mixed in with baby galaxies. But we do not see that. We only see baby galaxies long ago and far away. So the Goods Field South that we described a bit, this was presented at the AAS conference, American Astronomical Society conference in January 2010. I had an interesting time seeing this. They printed this out and put it on a wall at high resolution. It was about 30 feet long, I think, and about 15 feet high. It was an enormous, enormous poster that they printed out. But the goal with this thing was, again, to show that the images of that galaxies could be seen when we look perpendicular to the plane of the Milky Way. And as we look very, very far deep out, we get to see how galaxies have evolved with time. And here are some details from that image set. As we zoom in, we see many, many galaxies, but the deepest, tiniest, even the tiny little flecks, those are galaxies. Those are, because they're misshapen and they don't look like point sources such as stars. Now, there are a few Milky Way stars in this image, quite a few, but most of them are, but there's more galaxies than stars. So the fuzzy objects are galaxies. And on the left-hand side, we see a number of tiny galaxies or globular clusters or dwarf kinds that are that are interacting with the two near spirals that we see. And we see kind of a little spiral off to the upper left that is much further away. And here's some details inside of that as well. We see a kind of a cluster and some gravitational lensing effects. On the upper left there, we see a gravitationally lensed galaxy. And we see the ranges of redshifts in here. So if you can go, I will post the actual images and the location where you can find this on NASA's website, so you can go take a peruse so you can see how far back in time we look. All right, these are some really cool images. And again, almost all of the things that we see in this image are galaxies as opposed to stars. But part of the ultra deep field that was observed were some extraordinarily high redshift objects. So in 2011, a particular ultra distant object was seen where its redshift was measured in a very special way, which I'll describe in just a bit. And if it is a tiny, dim, misshapen, compact galaxy just made up of blue stars, wait a second, if it's made of blue stars, why would it be red in the image? Well, okay, since it's not like a mystery game, it's red because it's been redshifted. It's been redshifted deep into the infrared. But in order for it to be seen deep in the infrared, it must be extraordinarily bright. And if it's high redshift and still visible in the infrared, then therefore it must be bright. And therefore whatever was emitting it was emitting copious amounts of blue light. So this is a time when this particular galaxy, whatever it looked like, was a mishmash of stellar activity. So let's zoom in and take a look at what this ultra deep object is. It has the highly enjoyable name of Ultra Deep Field J 395-46284. Okay, that's not very illuminating. This was done by Illingsworth at Santa Cruz and Bowens and Hubble Ultra Deep Field 2019. And so we can zoom in and see this little bitty tiny red dot, which is this ultra high redshift object. And well, now we're looking at the actual pixels on board the Hubble Space Telescope itself, and that is the pixelation, that blocky appearance is the appearance of the actual object in the picture itself, and the boxes are the individual pixels on the camera for the Hubble Space Telescope. And I provide a couple of links here that show an interesting thing we're going to talk about called photometric redshift. So photometric redshift is what you can do when you have a high redshift object and a lot of filters. So the Hubble Space Telescope is outfitted with a huge number of filters that it can use to put in front of the camera. So what they'll do is they'll focus on an object and then they'll take an image of it with one filter, then another, then another, then another. And if you steady on it and look at, now we've got this funny thing going back and forth, okay? So what we're seeing is an image of a galaxy, and if it's red shifted, it will simply disappear from the long wavelength, the short wavelength, meaning the purple and blue side of this, which would be the left-hand side. And as it's getting redshifted, it will appear only on the right. So why does the light disappear and go to zero? That's because there's hydrogen gas in the way. And as the light traverses the distance of the cosmos, as it traverses it, the hydrogen gas absorbs it at a specific frequency, but it's been redshifted, so it gets absorbed at every wavelength in between. So you're going to find that there is no light left over at visible wavelengths because as it travels, it keeps passing through hydrogen gas at different redshifts so it can absorb at different wavelengths. That's really interesting. So we're left with, if you only see it in the longest possible wavelength band filter, and that's the only signal is in the long wavelength filters such as the F160W that we see there, way off on the right-hand side, and it's only visible in that one. That means it's been so strongly redshifted that the only way that galaxy can be seen is if it's a redshift exceeding that of 10 or 11. All right, so an example galaxy then, the Hubble Ultra Deep Field, the Hubble Ultra Deep Field 2009, and the Extreme Hubble Deep Field, which is XDF, actually integrated all these things together and looked at all the various filters that the Hubble Space Telescope can see, stacked them together, and found that 395-46284 Ultra Deep Field J object has a Z or a redshift of about 10 because it only appears in the Hubble H filter. It doesn't appear in BV, I, Z, Y, or J filters. And so we call this a photometric redshift because the galaxy's light only appears at that wavelength. So we think it's a galaxy and not a foreground star because a star will still have some emission at a little bit broader wavelengths. So it won't be only at these wavelengths. Although it could mirror that, but then you look at the shape of the object and say, oh, it's misshapen, it doesn't have a point-like source. So therefore, it's probably not a star or some rogue planet in between the galaxies, because those things would be pretty dim. And so the galaxy itself can be observed And we can posit that because it only appears in one of the filters, it must be at extraordinarily high redshift, and therefore it set a record of being a redshift of 10 when the universe was 10 times smaller, more like 11 times smaller, actually. So the Hubble Ultra Deep Field was then concluded in 2012, and those observations were taken between August and September, and that included numerous observations on top of it all, and using the Wide Field Camera 3 with numbers of different filters. So they actually started adding different filters together, and the goal would be then to say, if you can add all these filters up, you can finally get photometric redshifts, and that's what's been highlighted in this image is the highest redshift objects in the entire field. And we see that there's a couple of them at high redshift 8, another one at 10. Inside this field, another tiny object at redshift 9.5, and another high redshift object at 8. At almost 9-ish, and then the highest redshift object is the one we were talking about at 11.9, which is an enormous time, which is when the universe was 1/10 of its current age, or 1/12 of its current age, and 10 times smaller. Remember, we talked about redshift indicates the size of the cosmos, so it's actually about 12 times physically smaller at that time. So the extreme deep field then stacked all of these images together and made it for an amazing panorama. They took all the legacy data and all their own current data and pulled it together to make one image, so it actually had many months of time. And this is a common technique that amateur astronomers use in order to stack images together to make a very pretty picture, and it actually cleans up the image because you can actually eliminate noise by doing that. So the more data you have, the cleaner your data is, and you can say, oh, you have a pixel in this image, but not in that image, and so that must be its noise. And so this allows the image to be very well cleaned, and the only thing that's left is data. So this one small image shows 5,500 galaxies at various states in evolution. And we see there's the proof, and that we have some extraordinarily distant objects, and there was one that showed a redshift, a supernova in a galaxy inside the Hubble Deep Field, which demonstrated the redshift was at a redshift of 2. So that was a very high redshift object to see. All right, but that's not all. So people kept hunting and hunting and hunting, and eventually found inside that field some objects that are worth following up on. And the Hubble Space Telescope, led by Pascal Oesch at Yale, in March of 2016, instead of just doing a photometric redshift, obtained an actual spectroscopic redshift inside of the most distant galaxy. So that is this is a much more difficult measurement. Photometric redshift has a lot of problems, but if you can make an actual spectrum of it, then you know that you're actually looking what you can actually determine the spectral characteristics and determine it's actually a galaxy and not a star. So they were able to do this and find that this was a confirmed redshift by actual spectroscopy. That when the universe, we're looking that the light has traveled to us from this little galaxy for 13.4 billion years, and only when the couple hundred million years after stars first started to form. So we're almost looking at the very baby pictures of the universe. And so this is an amazing little discovery. And so you had to really pore over this image to say, hey, there's a very red-like object. Let's take a closer look at it. And so here is the image of that. So they cleaned up the Hubble image. We saw from the other thing what it actually looks like. And we see this squarey aspect to it, which shows we're looking at the actual pixels of the Hubble Space Telescope. And this is the shape of this misshapen, really bright galaxy. Well, it was very bright at its time, making huge amounts of blue stars. It now looks red because of the redshift. And so it probably existed, the time it existed about 400 million years after the Big Bang. And so how they did this was they took the spectroscopic slit of the Hubble Space Telescope and laid it across the object. And that's what these lines show, is the location of how the orientation of the spectrometer was. And so they actually could get some clear space in order to actually get a view of it. And so what they had to do is they took their full spectrum of it. That's what the top image shows. And then they figured out, well, there were some bright objects in there, so they must be contaminating a little bit. So they reduced the contamination by the objects there. And after they take out the contamination due to neighbors, then they had a clean spectrum. And then they had a model of what a high redshift galaxy should look like. And then they reduced the clean spectrum by the model, and they got what looks like static. And that bottom one is the residual, which is static. And so that's the best you can do, is create static, which is random noise. And so they feel like they've actually gotten it. And so since this spectrum took 12 orbits over 3 days of focusing on this one little object, they found that they could model the spectrum. So the upper portion is the actual spectrum of it. And then the modeling shows where the data points lied and how they could actually say, okay, it's basically noise to the left, and then they have an actual spectrum that begins with the GRISM showing it's an 11.1 redshift object. So this was it is currently the highest redshift object measured spectroscopically, which is really interesting. So it's the farthest galaxy that Hubble probably will be able to see, and it still doesn't get to when stars turned on. It's looking at extraordinarily deep objects, but Hubble's aperture is not large enough. It simply is not a large enough aperture, and it doesn't have the infrared capability. And that's going to have to wait till the James Webb Space Telescope is launched. So the previous record holder was about 700 million years after the Big Bang. Now it's something that's looking at about 400 million years after the Big Bang, just after stars started forming, only 200 million years. So we could think that if stars that are supermassive take only 5 to 10 million years to actually form, then potentially we're looking at the first 4 or 5 or 6 generations of stars being formed in that misshapen sort of weird galaxy. And hopefully the James Webb Space Telescope will be able to see things. And this diagram kind of shows us what we've been seeing, is that structure forms with time, and galaxies evolve from being small, misshapen, tiny, bright things, and they merge and collide into larger and larger and larger objects until they form either supermassive ellipticals or small ellipticals or grand spiral galaxies. So just to give you a feel for where this location is, where that tiny, tiny, tiny galaxy is, we're looking at Ursa Major, the Big Dipper in the sky, and so let's zoom in to see how tiny a patch of sky that really is that we're looking at. And we keep zooming in and falling into this tiny patch, into the Goodsfield North survey, all the way into tinier, tiny locations, and there it is, one little bitty object seen and observed spectroscopically by Hubble. And yeah, it's right off the handle of the Big Dipper. So what we've learned by looking at these deep, deep, deep surveys, which we'll call pencil beam surveys, like the Hubble Deep Field, Hubble Ultra Deep Field, Extreme Deep Field, is that we're able to see galaxies in different states of evolution. And so we can think of what a spiral galaxy like our Milky Way would look like. And it would when the universe was only 2 billion years old, is what the far right-hand pictures might see. And as time progresses from, say, right to left, I wish it was the other way, but hey, we're going this way. So when the universe is only 2 billion years old on the far right, things were tiny, bright, and misshapen. And as at 5 billion years after the Big Bang, we see multiple cores and multiple interactions in some bright areas, but not uniformly bright across the object, but they're larger and there's some structure that's appearing. By 9 billion years after the Big Bang, objects have gotten much more complex and larger in scope. And by the today type time, 13.7 billion years later, we're rounding to 14 just because this was in 1994. And still, the dark energy still not been really discovered yet. So here we go. But 14 billion years, 13.7 billion years later, I should really adjust this slide, we see spirals and giant elliptical type objects. So galaxies evolve with time. We do not see Milky Ways in the deep past, so therefore a key prediction of the Big Bang, which is stuff had a beginning, it evolved with time, and we only see very far away long ago because it takes time for light to get here from there. So therefore, since we don't see structured Milky Ways deep in the past, there the universe had a birthday, and we're seeing the tiny, tiny, tiny beginnings and how things evolve with time. And that's what the important thing is, and a key prediction of the Big Bang. Now, if the universe was infinitely old and infinitely big, and maybe there's matter being created like a steady state theory, then you should expect it to be mixed together, like young galaxies, like tiny misshapen things right next to old ones. But that is not the case. We only see the tiny misshapen bright ones deep in the past. We only see the grand spirals nearby. We only see the giant ellipticals nearby. So galaxies do evolve with time, and that is a key prediction of the Big Bang theory. So there's some review questions for you to go over and talk about, and I'll post the links to these websites, which are really amazing, so you can learn even more about them on my website and on the YouTube channel. So we'll see you next time.